everybody. Welcome to the overview talks here at MSys. It's a nice tradition that was started in Klagenfurt at the ACM Multimedia Systems. And it was such a great idea that we should actually inspire the community with some exceptional talks that are collecting information about what the field has been and what the field will become, and giving you inspiration for your future research and getting you in touch with the people who are conducting things that you may not be using every day. And this year it's my pleasure to invite 5 speakers for overview talks. And I hope that you enjoy the talks. And the first speaker up is Professor Géraldine Morin. She's associate professor in Toulouse, finished her PhD from Houston, studied as a postdoc in Berlin, and then went to Toulouse for the associate professorship. And she's working on 3D models. And you all know that in our community we have been done video streaming for basically forever, but times are changing and we need to expand our scope. And one of the things that I'm seeing in the future is that 3D of all kinds are going to come into our community and become one of the important kinds of content that we have to deal with. So I'm happy that Géraldine is here today and is going to give us ideas on how we can actually represent 3D scenes, because that's something where we are so far very limited in our thinking, and I hope we can learn a lot. So welcome, Géraldine.
Thank you for the introduction. It's a great pleasure to be here today. I'm really happy to talk today, and I really like the multimedia community for their open-mindedness. It's very characteristic that I'm a 3D person invited to give a talk in a system conference, and I really thank you for that. So what I'm going to talk about today are 3D models. And until 2000, the 3D models were really used in dedicated application or in dedicated tools. Like that model, you have the data system where you have 3D experts that are able to manipulate, create models, or in the animation companies like Pixar, you all know of, you have models and they are again experts. Navigate around, or you can also numerize your environment. You can have this online 3D content.
Wait.
Thanks a lot. And you can use this online 3D content to try now like clothes in a 3D website, or to try glasses here. You can visualize 3D content at home, in games, or online, visiting like reconstructed city, or even with 3D glasses now. And you can even print your 3D content, because you can now have your own factory at home and print your 3D object. So everything is there, but everything is not really ready, because, for example, this website has been on since 2008, and it's still not the main website of this company for advertising clothes. So we still need to develop more tools to really make this 3D content fluid as a multimedia content. So what would I like that you get out of my talk? I would like you to know a little better what 3D models you can find around, that I would say are on the shelf, know their advantages and their drawbacks, and see how you can adapt these 3D models to your needs, depending on your application. So I'm going to have 2 parts in my talk. One that really talks about the classical models that you can find in the 3D community, and another part that to give you 5 multimedia applications and show we adapted some models for this particular application. So how would you choose your 3D geometric model? First, your data, your 3D content comes from somewhere, and you are going to have your 3D data in a certain form. And then you are going to target an application. Of course, you may have some other non-geometric constraints. You may want to have some attributes, like you want to map some texture on your model, and therefore you need a parameterization. Or you want to have some structure of the model, or to add some semantic information on the model, and this is also going to come into play. So, which characteristics should you consider when you want to choose your model? First, First, you may want to have a discrete model or a continuous model. You want to have some topology or not. So what I will call here topology is when you have a model, you have some information that links the different parts of the model. You may want to have volume model or surface model, like BREP, boundary representation. And you may have a rigid model, or you may want to animate your model and to have something dynamic. So for example, if you want to model fire, then you want some discrete model. You probably don't want any topology because it's very fluid. You want a volume model for fire, and of course you want it to be dynamic. So what you would be advised to do if you want to model fire or any kind of fuzzy content is to take particle systems. I'll talk about it a little later. A second example is that you may want to model your new black motorcycle. So why do I say a black motorcycle? Because like a black car, when you have a motorcycle or a car, you certainly want to see very nice reflection on your car. And if you want very nice reflection, you probably don't want to have a discrete model of the car. You don't want your car to be piecewise linear, but you want a model where you can control the continuity of the model. You do want some topology, of course, you want something closed, and usually it's done with surface model, and probably you want it to be static with no deformation. So what I use usually in CAD systems are nerve-based representation. They are parametric models that you can edit with control points, and that gives you a smooth surface where you can control the geometry. So let's see now, after these two examples, an overview of these models. So in the discrete setting, you have the particle system that we have seen, and you also have point-based modeling. And these two sets of models do not have any topology, meaning that the points are independent from each other, and they are not linked. If you want some topology, you have meshes, more classically 2D meshes that represent a surface, or 3D meshes. And you may want to have something continuous, like in the second example, and for that, to ensure some smoothness, and for that, you have two settings, the parametric model, among them the standard nerve-based, or the implicit model. And you have a nice model here in between, subdivision surfaces. Doesn't work anymore. You have subdivision surfaces that make a link between the meshes and the parametric models, because we know that they converge to a smooth model. Okay, so a little bit more on particle systems. What are they? They are a set of particles that may interact or not. In the one I showed you before with the fire, they are independent particles. And they are usually well adapted to model fluids and all kinds of clouds on all kinds of volumetric fuzzy objects. They are quite easy to implement, and they are quite easy for dynamic, quite easy to use for dynamic objects. So here is an image of that has been done with Blender fluids. And you can also take your set of points and put them on a surface. So the advantage of points on the surface, they are called usually circles, like pixel is an element of a picture, a circle is an element of the surface. That's a point in space, and we usually associate with this point a radius and a normal vector. So there are some work, quite old already, on point-based surface so that you can have a multi-resolution of this point-based surface. And they have been actually first introduced by Marc Levoy that went to Florence to scan a lot of statues. And the resolution, he thought at some point, the resolution of the point surface is so low that indeed it doesn't really make sense to draw triangles around it. So here you can recognize one of the models that was scanned by the team of Marc Levoy in Florence on the right. And you have the advantages of point-based surface is that it's really the raw data that comes out of your scanner. And now with the different scans like LIDAR or time-of-flight cameras, we'll get more and more point-based models. Or even by multi-view reconstruction, you'll get points and attributes of colors. Here in this example, you see that the density of points have been adapted to the curvature so that it's well represented and you can decimate the points in the flat surface. There has been some work also by the team of Cobalt with Mario Botch that proposed to do, instead of round splats, ellipsis splats, and that gives a very compact model. So what you have on the left here is the model with the radius that has been divided by 2, so you can actually see the splats. And what you have on the right is the model that has been rendered with a splatting algorithm. So what is a splatting algorithm? It's an algorithm that you can implement on the GPU, and that is going to mix up the splats between the splats that come. So if you multiply all the radius by 2 on the left image, you'll see that there will be some overlaps on the splats, and your splatting algorithm is going to mix that to give you this smooth model on the right, or this smooth vision of the model, because the model is actually not smooth, but the rendering gives you a smooth impression. Okay, I'll talk again about splatting on the GPU afterwards. So if you don't have any topology, then the complexity of knowing who is around you, for example, in the splatting algorithm, by default is going to be O in the number of points of your model, which is not something acceptable. Hence, to ease the access to the neighbors, you usually use some space partitioning. So there are 3 classical space partitioning structures: octrees, KD trees, and BSP trees. So I won't talk here about BSP trees that share the space between against an arbitrary plane, because it may be unstable. So usually we prefer octrees or KD trees. So octrees, you probably know about them. You have a partition of the space. You have a square, and you split this square into 8 subsquares, and you have a regular octree if you split all the cells the same way. And if you have a regular octree, you can afford to have an access to any cell in constant time, which is very good, because now your request for neighbor is optimal. It's O of the number of neighbors you have. The drawback of that is that if you split uniformly, you may split in places where you actually do not have to. So usually people use adaptative octrees, where you only split on the places where you have information, or in our case 3D contents. And then you have to traverse to get to the right cell. You of course have to traverse the tree. If the tree is balanced, it's going to be log n, where n is the number of points. And you only split in the place where you have information. This is an example. You have a 3D object, and it's in an adaptative octree. You see it's an octree because all the cells of the same level are of the same size, and you refine in the places where you have information. Another way to partition your space is to use KD trees. And KD trees are good because they give you the guarantee that your tree is balanced, because the way they split is that they keep the same number of points left and right. So if you see on figure 1 here, you have a first split, a first vertical split, where you have the same number of points left and right. And then on the second one, each of these 2 cells is separated at a different location to keep the same number of points above and below. And this way, at the end, you have exactly 1 point on each cell on the fourth image here. So this is the famous Stanford rabbit, and it's split in a KB tree. So you see here that unlike before, unlike in the octree case, the cells are of different sizes, but you also have splits where you have 3D information. Okay. So now, let's go to representations that do have some topology. So I would very quickly talk about 3D meshes. They are used usually in the FEM community for finite element methods. And this is an example where you have some 3D model and you want to compute the flow around this 3D model. And therefore, you model the space around it using tetrahedras and hexahedras in green here. Usually what we work with are surface models. They are actually, most of them, so that's the most popular representation, that's piecewise linear, and usually, like for splatting, when you do some rendering, you can get the impression that models are smooth. Or if you refine them enough, and your triangles are very small, it also gives an impression of smoothness. But you don't have any guarantee on the smoothness. More classically, triangle meshes are used, like in this rabbit on the left for you, sorry. And more recently, people tend to use more and more quad mesh. They are better for texture mapping. So how do you code your mesh? You usually code the geometry, which is the position of the vertices, by giving a list of vertices. And you encode the faces. Here I put triangular faces, just as the list of index of the vertices. And this is when you want to code the file, but when you actually use your mesh, the classical representation to use is a half-edge structure representation. So now, if you want continuous model, and that was the case for the modeling of the motorcycle part, you may want to ask someone in mathematics if he can give you some continuous function. So is it enough to have a continuous function to get some guarantees on your geometric model, on the continuity of your geometric model? It is enough if the parameterization that links the analytic representation is good enough. So what does that mean to be good enough? Parameterization are good when the speed or at which the curve or the surface the speed you are going to, so the derivative, is near to constants. It's ideal if it's always speed 1, and it's very bad if the parameterization is irregular, so it stops. If the parameterization is irregular, you lose this link between the continuity of your function and the continuity of the geometric model. So just to get the ideas clear, I'll do a very simple example in 2D. If you go to these continuous functional models, you have the parametric setting, which is the most classical, and the implicit setting. And they have different properties. There are different advantages and different drawbacks. They are actually quite complementary. So what is a parametric representation? Let's now start in the affine plane, so just in the plane. And we have a function t, f of t, that takes a parameter, a real parameter, and associate two values, x and y. And if you take the value of the function over an arbitrary domain, you get a curve. So here you get the function cos t sine t, and you take 0, 2 pi as your domain, and you draw a circle. That's a parametric representation of the circle. You can also define your circle implicitly. So you define a potential function. At each point of the affine plane, you associate a value. Here the value is mostly the distance between a point and the center of the frame, except that it's offset by a radius, because I want to define the circle as the zero set of my potential function. So here the potential function, you know it well, it's x squared plus y squared minus 4. It defined implicitly the zero set is the circle of radius 2. And what are these representations good for? If you have a parametric representation, it's very easy to generate points on your model. So you sample your domain. Here you will take TI values on the interval 0 pi, and you will know that you map them to points that are on the circle. It seems obvious like this, but that's something that is going to be very hard to do with implicit models. What are implicit models good for? If you take a point in the plane, you can very easily, so I take a point xy, I can very easily decide if it's on the circle. I plug it into the equation and I look if it equals 0. Or I can even know if it's inside the circle or outside the circle. Conversely, it's very hard to do the same thing with a parametric model. Take a point A with coordinate xa and ya, and tell me if it lies on the curve. If I want to answer this question, then I have to solve this equation f of t equals xa, ya. That means I need to know if there exists some t such that f of t is actually giving me the point A as a return. And for implicit model, it is very hard to find points on the models. So if you want to find a point on the model, you actually have to solve the equation p of xy equals 0. So what are parametric models good for? They are good for sampling points, so you can easily discretize the surface. And for implicit model, they are good to know if you are on the model, inside or outside, so they are good for collision detection. And in particular, they are very good for ray tracing. So ray tracing is a rendering technique where you shoot a ray through a pixel within your scene, and you can then go along your ray and see when you intersect the implicit model. In both cases, you can have a guarantee on the smoothness of your model, knowing the smoothness of the function, and that's what is interesting here. So parametric models are the models that are used they embed the NURBS standard from the CAD industry. And implicit models, they are not used so often because of their problem of sampling points on the surface. But in 3D, you may have seen some models. This is retraced. You see that there are shadows and reflections. That's a scene, that's an image from implicit model. They are good to compute collision detection. So if we wait for the people from the rendering community to really give us the opportunity to do ray tracing in real time, probably implicit model will then have a new life. Okay, just a little bit on the classical parametric models. So parametric models are usually polynomial models or piecewise polynomial. They started in the 60s with Bezier curves. What are Bezier curves? They are just polynomial curves in a convenient basis where the coefficients in these bases are actually control points, like you see on the top here, P0, P1, P2, P3. And these control points give you an intuitive, they describe intuitively the shape. But if you move one of the control points on one of these two red curves, you are going to change the curve completely because they are polynomials, they are globally supported. So B-splines have come here so that they are piecewise polynomial and you don't have this global influence of a control point. If I move the control point on the right here, I just change the purple part of the curve. And once you know how to do curves, it's very easy to do surfaces using tensor product. And here you have a tensor product surface where you see the same effect. You have a control mesh, and you have a smooth surface described by this control mesh. So why are they so used in this CAD model? They give you an intuitive control through this mesh. You have few parameters because you see that these control points are the parameters of the model. And you have a control continuity. You can higher the degree to get the continuity you want. Usually you want C2 continuity to have smooth reflection lines that we talked about before. And the good news is that you have a link between the discrete models and the smooth models, which is given by subdivision surfaces. So you have a control mesh on the left, and you have a rule that shows you how you refine this control mesh to obtain something that converges to a smooth surface. This convergence is going to a C2 everywhere surface except at extraordinary points, that is points that have a different valence than 4. You can see some on the model here. And the good news also is that you can benefit from the implementation of subdivision surfaces by Pixar. They have been using subdivision surfaces since 1997. The first try was in this Jerry's Game movie that you may know. There was a picture at the beginning. That was the picture at the beginning. And they released their software in 2012 for everybody to use, for commercial and non-commercial use. And some people have used subdivision surfaces for 3D compression. They decimate the model, and they regenerate through regular subdivision a new model, which is multi-resolution. We'll see that a little later as well. So I've done a small overview, a rapid overview of the different models that are there. There is something I didn't talk about, are the skeleton-based surfaces, which is a good mix between parametric model, you have a parametric skeleton curve, and the implicit model, and you define the surface as being a certain distance through this curve. Okay, now I'm going to go to the second part of my talk to give you some application of 3D model in multimedia applications and to see which model we used and how we adapt these models for the application. The first one is about streaming 3D meshes. So the same way, it was funny to see this photo again when I prepared my talk because it has been a long time that I saw an image appear progressively like that. I think like system people are working well and bandwidth is not an issue for images anymore. But we would like to have the same effect as these for 3D models. We have been seen that subdivision surfaces can help us. And for that, we need multi-resolution property for 3D models. Of course, here you have two images of the Stanford rabbit at different depths. And if they are close, you want a refined model, but if they are far away, like this little rabbit on the right, it's enough to have the model that is on the top right. That's what it's rendered for, and you cannot see the difference with the left full resolution model here. And maybe you even want this different resolution on the same model, because if you are looking from one side, you want to have a refined model, but for the back of the model, you probably still want to have a closed surface, but you don't need the same resolution. So it's important to have something progressive, because you want to have, when you send your model or when you stream your model, you want to see it appear progressively. This is the multi-resolution wavelet transform based on the work that I've shown you before, and you have different resolution depending on the number of refinements you apply. One thing we did was to use something more progressive, where you have a progressive representation of the mesh that has been developed by Hugh Hoppy in his PhD a long time ago already, where some vertex split generate a more and more refined model. And you can actually send this vertex split along to stream your model and refine progressively. Of course, these vertex splits are dependent from each other, and you have DAG representation that can model the dependency of the vertex split. And what we have proposed is a strategy, for a streaming strategy, to improve the quality at the client, to improve the quality, the expected quality at the client. And this is, of course, taking care. Okay, you can have two different settings. One where you look at the overall quality of your model, or you can even have your quality depend on your viewpoint, like we talked about before. One thing we have done as well, and that has been shown in this. Sorry, this is not. This is accepted. This is published. Sorry. that has been shown in this conference is that you can also restrict the viewpoint to a given, what we call the camera path, so that you can, along this camera path, see the model and at the same time stream the model to the client. So for streaming 3D model, what did we want? We wanted a model that is good enough for our application. Mesh was enough, but we needed some multi-resolution or even some progressive mesh that can have a progressive model. And of course, because of this relative coding, you have to handle the dependency between the different chunks of your model. So, a second application is to model virtual plants in network virtual environment. Plants are important in our daily life. They are also important in virtual environments. And we wanted to model these plants. So we took a nut tree here, and the number of triangles is very high. So we want to decimate it the same way that we have done for meshes. But if you decimate this mesh with progressive meshes, you lose the connectivity. So you have topological incoherences because the triangles are very, the topology is lost along the way. So what we wanted to do is to use a different model, and for that, we used a skeleton-based model. That means each branch is a curve and has a certain radius around the curve. And what we propose is to do compression of this representation by taking all the branches that look similar, group them together, represent them as an average branch, and code first the instantiation parameter that maps this average branch at its actual location in the tree, and some differential details that get you the original branch. And if you do that, this is the data structure representation. You have the branch model on the top, on the left, and this branch model is instantiated at different places in the tree, and you have the details that actually get you the lossless compression. So here is the compression rate that we obtain for lossless compression. You can see that compared to a blind compression, they are very good, especially for the last one. So it's very common to use L system to model plants. They are, the plants that are generated are very regular, and this regularity gets catched by the compression algorithm here. That's why the compression rate is so high. The two other trees are trees that have been numerized by biologists and don't have that regularity. And if you want to do progressive representation, you have the same DAX structure that we had before, and we can reuse the streaming strategy that we have for progressive meshes. And you see that even with a few low representation of the model, a low-level representation of the model is already pretty good. So here we saw that we used a different representation, parametric curve and implicit radius, and we were able to provide a compact representation, but also a progressive representation for streaming again. Now I'm going to show you another application, and this time we have a 3D model that may be defined by a scan. We had a real 3D model, so we scanned it to have a virtual 3D model of it. So we could have done multi-view reconstruction, and what we get out is really a set of points. And we want to track this 3D model in a video. So we want to estimate the pose, that is the relative position of the camera and of the 3D object we know. So this is our 3D object. We represent it, we don't want to change the model, so we keep the 3D point model. We don't define any topology. You have the model in the left, a detail in the middle, and the splatting algorithm I have told you about before. That means an algorithm for rendering that is able to mix neighboring splats. So what do? we do two things. We have a method to reference the 3D object in an image relative to different keyframes that you see in the middle image. And we have an iterative tracking of the object through splatting motion vectors. So as we are tracking the object, we represent the displacement of the object through a motion field on the object, and we actually use the splatting algorithm to interpolate this motion field on the object. So the interpolation, as the splatting for rendering, the splatting here for motion vector is also done on the GPU. Okay. So here's the first video where you see the tracking. That's the video, and we superimpose the model on it so that you can see the quality of the tracking. And you see that it's quite robust, because even if we hide part of the model, we still get a pretty good tracking. And once you have the relative position of your object and of the camera, then it's just easy to augment your model. So there is this little guy sitting on the object now that is being applied the same relative pose that our model. So what we did is to adapt this, to take this raw set of points and to adapt some rendering algorithm for point matching, and our approach is robust. And what we should have done, but time is always too short, is that because we don't have any topology on our model, it could be very easy to apply that to deformable objects. I mean, very easy. It could be possible. At least we could break the object into two, and that should still work. Okay. I'm going to, I run a little bit out of time. I'm going to pass very quickly on this fourth part, which is some structure. I think it's important to talk a little bit about structure, because now 3D models are also being analyzed, and structure of 3D model is important for editing. So that's some work that, don't be frustrated, I'll go quite quickly, but that's some work that we did to find the different symmetries or partial similarities between a model, which is nice for editing, consistent editing for the model, and we're also using for indexing the model, finding like similar objects in the database. So finding the similarity and identifying similarity in the model could be, of course, very good to compress the model, to add some semantic. If you change one arm in your character model, you probably want to change the other arm in a similar way, and to find the structure if you want to, for example, change the head of a person or swap the head of a person. And that has been done for chair or editing furniture. And now that I'm finishing my talk on 3D model, I have a small teaser to ask you, indeed, do we really need some 3D in the models? Well, actually, now I've been talking for a long time, and if I stayed almost always at the same place in this room, so I almost always got the same view of the room. And if you go to the movie theater, you put your 3D glasses, and you don't have 3D, when you say you see a movie in 3D, it's just two images that you see with your glasses, because your viewpoint is not changing much. So if the viewpoint is not changing much, probably a full 3D model is maybe not necessary. So if you actually follow a camera path, like I showed you before, probably someone can give you a video instead of 3D, right? But as you are system people, you know that, like, if you ask a server to render the video for everybody, it's not a scalable solution. So our idea on this work was to use some users with a lot of resources. They have good computers and good bandwidth, can maybe make some rendering work for users that have lighter resources, like they have a phone and they have a lower bandwidth. And is there enough users to do that? If you go to Second Life, there are probably enough users to do that because it has been shown that around in popular areas, the number of people is high enough. So what are these not 3D representation? These 2D representation trying to model 3D have been used for a long time. There are billboards, and now it's very common to add to your image representation a depth information. And if you have the image representation and the depth information, you can use what is called the warping algorithm, which is already quite old, from 95, from Macmillan and Bishop. And you can change your viewpoint to another view. Of course, there will be some occlusion issues, but if you take multiple source images, that will overcome these occlusion issues. So what we have proposed here in work with Singapore, that was the PhD of Ming-Hui Zhu, is to create a binary image-based representation that we store in an octree. So if you have someone that has been rendering part of the model, you are going to store this part of the model into an octree at the actual 3D location. So when the person renders, he has the pixels and he has the depth information. So you know where to put it in the octree. And if you have neighboring pixels, they may come in the same cell here. But if you have different pixels from the same image that come into a different cell here, we can still code them in what we call a sprite, and store them in the sprite tree. As a matter of fact, now this representation is viewpoint dependent. So for the same object here, you will have different sprites in the sprite tree depending on the viewpoint you have from this object. And once you have stored from your user that have a lot of bandwidth, you benefit from their rendering, you store it in the sprite tree, and for your light user, he can access the sprite tree and render from the sprite tree. So here is a reconstructed image. We have a background image, and that's what happens in the foreground. In the foreground, you have different sprites that you see around the image, and you warp these sprites to obtain the image in the middle here. And what you get from your rendering on the left is the rendering from the sprite tree. On the right, you have the ground truth. And here, you have the rendering time when you implement the rendering from the sprite tree on the GPU as well. So rendering from 3D geometry is, I cannot say it's twice slower, but it's still slower than rendering from the sprite tree. And the quality is quite comparable, especially when you look on a video projector here. It's very hard to see a difference. You can see a little bit in a difference in the plants here, because you see a little bit the fuzziness of the splats, actually. Okay. So what do we get from there? So we get that, in fact, our 3D model can be implemented also as an image. So there is a compromise to be found between the geometry and the texture. Especially if your viewpoint is not changing, you can swap, or not changing match, or you can control it. You can swap your 3D model for RGBD model. And this depends, of course, on the navigation you will have around your 3D scene. So if you know the navigation and you can know where people are going, you may benefit from not representing fully the 3D models. The question you should ask yourself is, how much 3D do I really need? And can I predict the navigation or the interaction of people with the 3D content? Okay, so I'm going to finish my talk here. I hope I gave you a feel of the 3D models that are on shelf and that you could use, and that you may want or need to adapt your 3D models. I think that because of this new trend in sensors and in the manipulation of 3D models, 3D models are also bound to evolve. Of course, we see already today that there are more and more 3D point clouds, and there are new reconstruction primitives in computer vision. You have classically people reconstructing points, but they are starting to reconstruct segments or to reconstruct planes. And you also have people, I told you here, for me, topology was just a mesh, 2D or 3D mesh. But you have some people that are working in simplices that open the way for not only surface, but surface and volumetric representation. And this is good because 3D printing is all about 3D models. Of course, you can give your 3D printer a surface representation, but your printer is going to have to choose how he fills the model. It fills the model. And maybe you want to choose how to fill the model because you want to control the weight of your model or the balance of your model. And it's going to be very important to have this volume representation. So thank you for your attention. And I'll be happy to take some questions.
Yeah, are there any questions? Uchi?
Hello. Hey. This might be a naive question. Are you aware of any works that combine multiple models? I guess I'm thinking about some of the video games that have more or less static models, but then might have like fire and things like that, and then the implications that might have on doing things like streaming of such scenes.
Yeah, so I think you are right. It's because you want to adapt your model in your 3D scene. You have model of different nature. That's what we saw for the plants. We chose to model the plants with this generalized cylinder representation, but for sure it's not possible. So in general, the 3D objects have skeleton surfaces. So it's certainly a good idea to have different models. Actually, in Pixar movies, all the animated characters are subdivision surfaces, and all the static stuff are NURBS-based models. So they also have these dual things. And most of the time, also in rendering in 3D scene modeler, you can have particle systems. If you want to have smoke or fluid, you will need this particle system. So I think, yes, it would be very important it's very important to support different models within the same environment. And as you said, it's going to have different constraints for static or dynamic models. So mixing models is definitely important.
Is there another question? I have been wondering one thing. You just came back to particle models, but you started the talk with that. And in many cases, we want to record and transfer something from the real world. And to have once, I think, seen something in the multimedia community where you actually have derived the particle system from an observation in the real world model. Do you think that's something realistic to do in many contexts?
That's a tough question. So, the particle system that I show for fire is very easy to implement because there is no interaction between particles. And now you have this model that I've been modeling like deformable objects that also use particles. So you have to very carefully see the interaction between particles, and it's becoming difficult. And I think most of the work on particle systems, you generate some behavior looking at, like, you integrate some behavior, and I'm not sure this behavior is really modeling some physical properties, actually. So I'm not aware of work that would analyze the behavior of some particle system and be able to regenerate the rules that are, yeah, so. But of course, that would be very interesting. But it's a very, I think particle systems are like this kind of system that are probably not very stable, right? So analyzing unstable behavior. We are getting pretty good about weather, so maybe.
All right. Thank you very much again. next speaker is Rangel Egg. She is teaching at a school for students that learn marketing. But for that, she's using her expertise in perceptual psychology. She has both her master and her PhD in psychology, but she has actually worked for quite a few years with the multimedia community to find out how well we represent multimedia content from the systems perspective. So there is a context switch. When you come from psychology, you tend to look at the effect of the human perceptual system at a very low level of detail. So do we see a flashing light? When we go to multimedia, we want to know, does this video encoding work perfectly, or how well does it work? But the stretch between is so big that you actually need to spend quite a bit of time on working on that. And that's what Rangel has been doing for quite a few years. And right now, she's looking into interactions, and she's going to give us an overview talk about how the state of the art is on that. Please, you can go ahead when you're ready.
Thank you, Karsten. And good morning, everyone. So I really appreciate that introduction, because that saves me a bit of explaining on this talk. Because I will talk about human-computer interactions, and specifically interaction between motor inputs and visual outputs. So we'll just ignore quite a few modalities for the time being and just focus on what we can see and what we do. And what happens when delays occur between these two events. So what we're basically trying to do when we interact with a system is to use our senses that have been evolved to operate within the physical world with all the physical laws that we adhere to. And then we try to mimic the physical world in a digital world, which sometimes goes according to plan and sometimes it does not. And what can happen? Well, delays, among very many other things. So delays is something that we are used to, but maybe not to the extent that a system can impose on us. And my bold claim is that nobody likes waiting. I do not like waiting, yet I do it all the time. I do it whenever I hit a button on my computer. Because machines, they do keep us waiting, don't they? All the time, constantly and continuously. And we accept it, we even expect it to happen. And normally we do not even notice, fortunately. Because it is a fact that all systems have delay. And most of it is unnoticeable. Even without a network, we have delays. And this is from Kjetil Rohn and Andreas Petlund. They actually set forth to try and measure how much system delay do we operate with every day. So it's a very, very simple presentation. It's a square presented on a screen, and you have a mouse. You hit the mouse, the square appears, and you have an oscilloscope that measures how long it takes before this square appears. And then they also had a game, Unreal Tournament, and just a simple gunshot in that game to see how long does it take from hitting the mouse button until something happens. And in the very, very best scenario here, it took 23 milliseconds. That's with vertical synchronization turned off and no network latency, just a closed loop. And then they, of course, did it repeatedly, so the average here is far worse. And you start seeing values from 30 milliseconds upwards. And then we know that this is the best case scenario, right? But fortunately, our neural processes, they're not instantaneous either. It takes time for sensory signals to travel to the brain and to be processed and then integrated. And well, networks. We all know what happens when you transmit signals across a network. We know from frustrating experiences, and I guess many of you know that from your research as well. So this is what I'm going to delve into, and I'll spend most of the time talking about perception, and I'll explain that to begin with. And then in the end I will also mention how these delays, motor visual delays, can actually influence performance as well as enjoyment. Right. And I'll be mixing jargons a bit here because I'm actually deriving this information from different fields. So you have the HCI community, you have multimedia communities, and of course psychology. So I'll be going a bit back and forth, but I'll try to make it all clear. Just wave at me if you don't understand. So perception, because perceiving is believing. Perception is more than just sensory signals. It's actually making sense of what our senses process. So we're making sense of the world continuously, and we do it effortlessly. But how does that actually happen? Psychologists, they were talking about the binding problem decades ago. Then they were talking just about visual perception, but it applies very much to multisensory integration. So trying to make sense of several senses at the same time, because we do not perceive the world one sense at a time. Me standing here talking is a multisensory experience. So I quite like this little cartoon here with this man who's being controlled by these different fellows. You have one responsible for the sense of smell, one is for the gustatory sense, so taste, vision, hearing, etc. But these guys, whereas they are specialized in their different domains, they interact. They run around this little head and they interact and transmit information. And this is a viewpoint that psychologists held for years, that the brain is modular. So we have these specialized areas that process sensory information, but they integrate at some point. So this is the binding problem. How does this happen? And why are we not even aware of it happening? So we have a very flexible perceptual system. We have different senses that transmit information, whether it be from sensory receptors in the skin or the nose, or from our vision or hearing, and they go across different neural pathways, and finally they make it to the brain, and then we have these specialized areas. And somehow this is all integrated, all good and well. But recently we found out the brain is modular, but it is in fact also continuously integrated. So we found multisensory neurons in areas previously believed to be a visual area. So all this integration happens continuously, while at the same time the senses are processed in parallel. So integrating what we see, what we hear, what we do is much, much more complex than we actually were aware of. But fortunately, it just happens. We can just accept it and be grateful that we have a flexible brain, because it helps us. When we are exposed to delays, it has a buffer. So this mechanism, this integrated mechanism, helps us compensate for these delays that we're exposed to. And in this talk, we'll focus on the motor visual delays. So, for instance, hitting a button and waiting for something to happen on screen. And as long as we stay within certain thresholds, we don't even notice them, because our brain takes care of it. And I'm going to make a distinction between feeling something, so the tactile sense, because that is passive. We can be exposed to tactile stimulation and then try to decide whether what we're seeing and what we're feeling is happening at the same time. But then we can also add the complexity of intent and kinesthetic information. So actually doing something is quite different from just feeling something. And I'll explain what I mean. So in one case, just feeling something on your skin or your fingertip makes you a recipient. You're receiving sensory information, and it's just involving sensory signals. And it's a single task. If you're asked to discern between what you see and what you feel, you're just doing that. You're saying, well, I felt that before I saw it, or vice versa. And when we do find thresholds between this, how little time can pass before you start noticing the difference, these temporal thresholds are very short. But when you add an action, we become active. We're actors or agents in a process. We have intent and we have purpose. And then suddenly we have motor signals involved in this. And we get two tasks. We have to provide an input, and then we have to discern, was there a delay here or not? And these thresholds are typically very much longer. So we have, on the one side, perceived simultaneity or synchrony. Does this happen at the same time? Or we have the sense of agency. Am I the agent causing this thing to happen? So just to have a look at how different these results can be, I just gathered these studies. So you see that just feeling something and seeing it, if you want to distinguish between these two, we're talking about discrepancies of less than 100 milliseconds, even as far down as 29 at the most sensitive a human being can be. But if we're adding action, then we're quite more tolerant. Because we expect a delay. We expect that when I do something, it's not going to happen instantaneously. There's going to be a slight delay. And so a lot of researchers do work on this, and they apply various methods in order to establish just how much time can pass before something visual happens without it disturbing the interaction. And so it could be response time, how long does it take for me to react to that and to do a subsequent action. It could be temporal order, so just asking someone what came first, the key press or what you saw. It could be adjustment, trying to adjust it down to the point of no detection. Discrimination, saying again, is this synchronous or is it not? Could be temporal order. So many of these, they overlap and they tend to address the same thing, but they ask different questions. So temporal order, you ask, was the key press first? Yes, no. And then we have all these more cognitive notions of sense of agency or estimating time interval. So I'm going to give a few examples of research using these different experimental procedures just to see how different the results can yield. So temporal order, I'm going to start with the most complicated, so we just finished that. In this case, you just press a button and you wait for a flash. And so you do this, either in the controlled conditions, you just have a system delay, 35 milliseconds, or you add, on top of that, 100 millisecond of delay. Press the button, wait for the flash. And you do this again and again and again and again. And every time you ask, which came first, the key press or the flash? Well, if this is consistent enough and happens repeatedly, we start adapting to it. So in this case, 60% of the trials has the same delay. In the experimental condition is 135 millisecond delay, 60% of the trials. If you start adapting to that, you start noticing the flash earlier, or you start shrinking the such time interval. And so you have temporal adaptation. And you get fancy results like these. But what you notice here is that the red curve is shifted so that you are actually reporting the key press to happen before the flash, later stages. So you're noticing the flash far sooner because you've been continuously exposed to this delay. So the perceptual system is flexible and dynamic. That means it can actually help you in these situations where the lag is constant. Even to the point where even when the flash happens after the key press, you start perceiving it as happening before. So you're pressing the button, but before you even do that, you see the flash. It's quite fascinating. And similar kind of setup with a key press and a flash. And you're asking people to first do the temporal order. Was the key press first or was the flash first? And people start learning the procedure, and then you ask one group whether they felt like they were the agent, whether they were causing the flash. And then you ask the other group, did this happen simultaneously or not? And you can see then the difference between these two measures. If you're asking people whether they are the agent, that's the pink bar, they have a far more tolerant temporal window. So this extension of the window represents how long they are actually perceiving to be in charge of the event. So when the flash happens after, that's the graph on the right, they are more tolerant to the delay than the group that is asked whether this happens at the same time. So these are two very different ways of measuring how tolerant we are to the delays. Another way is just to ask people to estimate time interval. So very simple setup. You have an object on screen and you have a joystick. You press the joystick up or you press the joystick down, and then the object moves. Sometimes it will move consistently with your actions, so it will move up when you put the joystick up. Sometimes it will move inconsistently, so it will go in the opposite direction. And then you ask people to notice the time delay. So you push the button or the joystick, the object moves, hopefully in the direction that you wanted. How long time did you have to wait before the object moved? Well, not surprisingly, the estimated time intervals, they increase as the actual delay increases. But for very short delays, 100 milliseconds, people are not able to estimate just how long that is. So they actually perceive that they're waiting far longer than they are in reality, close to 300 or 250 milliseconds. And then of course it varies whether it's consistent with their action or inconsistent. So if it happens as they expect it to happen, the time interval is shrunk again. Because we're talking about agency, a feeling like we're in charge. If the object doesn't obey us, well, that contributes to decrease that sense of agency along with the delay. So you see this interaction between delay and consistency. And as the delay increases, well, we become better at guessing how long we have to wait. And these authors, they actually call it authorship, but asking them then after this, how much in charge did you feel? You can also see that goes down with increasing delay values. Another fascinating thing is that we become better at this as we age. We gain experience from knowing that our actions lead to effects, because we do it continuously. So we become trained, and our perceptual system is trained along with us. And it's not like every single interaction we do in life is transparent. Sometimes there's a lot of noise and things happen, so we learn to surmise what comes in between is just disturbances, and this is the actual effect that I'm looking for. And sense of agency is strengthened. So again, this notion that I'm the agent of this effect. So these guys actually did a study on this. So you have this little funny game here where all these X's and O's are traveling downwards, and you can move the little white square across the gray line to try to catch the O's and avoid the X's. Very simple game. Except, of course, there's a delay here. So you have to compensate for the delay, and you have to try to play the game. And the delays can be quite large. It's either 250 milliseconds or 500 milliseconds. And there's also some condition they call turbulence. Still delay, but it's random. So they have two values here, and they're sort of trying to map that with the same lag values, but it varies. So you have no idea how much delay is following your input. And so they test children, they test college students, and they test older adults. For some reason, they're not consistent in their way of reporting ages, but these are the mean ages, and the age range for college students is 18 to 24 years. So what do we find? Well, children, they're not that good at judging their sense of agency. So generally, they perceive a reduction in their sense of agency regardless of what kind of disturbance we introduce. So there's lag or there's turbulence, it causes a reduction in their sense of agency, not surprisingly. College students seem to be the most affected by this turbulence, this unpredictable delay. And they're also quite aware of themselves being the agent, but this lag and this turbulence is disturbing their perception. Unlike older adults, that seem almost unaffected by it. They know they're causing this, and they are able to predict that, despite all this disturbance in the temporal domain. So, performance, because timing does matter when we have to perform on a computer or on any other kind of system. We are continuously interacting through key presses, mouse clicks, whatnot. And if that doesn't happen instantaneously, well, then we have to compensate, and that can affect our performance. So this is an obstacle avoidance task, it's called. So you're simply using a mouse cursor that can only move vertically, try to get through this field without touching one of these objects. You're avoiding all obstacles, basically. And as before, there is, of course, a delay. So you're moving, but you have to compensate for this 235 millisecond delay. Notice that many of these studies, they do use quite high, long temporal delays in order to see the effect, which makes it hard to predict what effect smaller delays have, but I'm going to get back to that. So here we have 235 milliseconds, and we have 10 participants, or subjects as they sometimes refer to them. And these guys, they first play the game with just a system delay, which is 35 milliseconds here. And then they try to increase the speed, so they're playing the game continuously, or repeatedly, more rapidly. And then they try to see what the top speed is, and they play it until they get to the point where they manage 4 out of 5 trials. And after that, if they fail, the last round is their top speed. So they basically establish this comparison ground, and then they insert delay and let them play again up till the same previously established top speed, and see how many of these trials they will succeed at. So you can see, even though one person in the post-test managed 60% of the trials, the rest of the group, they are severely affected by this delay. So on average, you have a 32% managing to complete this trial at their previous top speed. So that's a quite an obvious detriment to performance. And these guys, they design their own game, 3D game, a platform game, where you follow a path, you avoid lasers, and you collect gems. Straightforward, entertaining. And of course, we have delay, again, disturbing your performance on this task. But instead of actually measuring performance, they ask participants various questions, and one of these questions addressed just how easy it was to control the avatar. So these are participants' perception of control, their perception of actually being in charge and playing the game well. And you have to get to 500 milliseconds of latency before they feel like it's harder to control the avatar. So the other delay values, 50, 100, 200, 300 milliseconds, doesn't seem to affect their conscious experience of control. And they had 3 levels of this game. So each one of these delay values is one group. So they're only playing the game 3 times. And number 1 and number 3 is exactly the same. And the reason for this is to see whether they have a learning effect. Can they actually learn to play the game better with experience? And yes, they do. So they subtract the ease of control from the last level, from the first level, from the last level. So they look at the difference between the first and the second or the third time they play the game at the same delay value. And what they find, okay, the guys playing without delay, they are far better in the last round. But also the guys that have quite the high delay values, they're learning to compensate for this delay, and it feels easier to control the avatar because they've done it before. So we wanted to see the actual effect on performance and also design the game for a more simple game. So this is what we call puck hunt. This is a black ball bouncing around in a room, and you use your cursor, you move the mouse to move the cursor, and you try to catch the bouncing ball. Straightforward. So of course, the cursor lags, and the click you use to catch it also lags. So the delay is constant in the movements of the mouse and the click. And it varies from trial to trial. So you're playing this game repeatedly, I think 120 rounds. And then we time it. How long does it take participants to actually catch the ball, depending on the delay? And so we did this study both in Worcester and in Oslo, but with different systems come different inherent delays. So I'm just going to present the Oslo results. So the ball is actually bouncing at different rates. So it's going very fast, which is the blue curve, slightly less fast or quite slow, which is the red curve. And of course, the faster the ball is bouncing, the harder it is to catch it. So you can see on the y-axis, you can see the median time it takes in seconds to catch the ball. On the x-axis, you can see the delay we inserted. So there's a nice interaction here between delay and between the pace of the ball. It becomes difficult with delay, and it becomes difficult as the ball speeds up. And that is quite evident from 200 milliseconds delay in this graph. But zooming in, we can actually see that it starts much sooner. Delay has an impact on performance, maybe even from 50, 75 milliseconds when the ball is moving at a rapid pace. So we can see from these results that depending on how we measure and what questions we ask or how we design the task, we get very different results. And this is quite symptomatic of all the research in this field. It's hard to just set a number on a threshold because they're all so different. Finally, enjoyment. Because if a user doesn't enjoy his experience, why will he come back? Why will he use your system again? Enjoyment is important, not just in games, even though that's what I'm talking about in the next few slides. So we're going to go back to the normal game, the ones that had the avatar avoiding lasers and collecting gems, because they also asked participants whether they enjoyed playing this game at different delay values. And mind you, these are different groups, so they only played at one of these delay values, so they all seem to enjoy it. Even the ones playing with half a second delay enjoyed the game. There are no significant differences in the data set here. But maybe that's just the phrasing of the question. This is a game, a 3D platform game. Maybe they really enjoyed the game and just disregarded the delay. But if you ask them whether they noticed the delay, well, certainly the ones in the 500 millisecond condition did notice it. 8 out of 10 people. Quite remarkable, 2 people did not even notice that. So if you ask them about the quality of the motion of the avatar, then you can see that there is an impact of delay. It's a small one. It's significant, but only at 500 milliseconds. So this is when we start to see, if you ask the right questions, maybe you'll get insight on how your user perceives playing with a delay. We also asked this question, but we pointed their attention to the delay, asking about the quality of the responsiveness of the game. Naturally, there's a vast difference between the game we designed and a 3D platform avatar game. So we addressed simply the responsiveness. And not surprisingly, we can see it decrease. As delay increases, well, logically, the rate of responsiveness goes down. So we know that we interact with systems in very different manners. And there are so many ways that we can input our requests. We can use our voice, we can use a keyboard, a mouse, joystick. And what we wish in return can also be quite different if we want to yield text or we want to calculate a budget or design a website. All these interactions have vast impact on how we can measure sensitivity to these motor visual delays. And what I'd like to see are comparison studies, because I've not succeeded in finding many people that try to explore the nature of the task and the interactive modality that you use in order to see whether that affects temporal sensitivity, because I imagine it would. But what we do know is that delays can be perceptible, they can be detrimental to performance, and they can be negative for a user's experience, but all above a certain threshold. You have to get to a certain delay value before it starts affecting us. And we prefer it to be constant and not fluctuating. If we have jitter, that could be far more annoying or far more detrimental to performance than a constant delay, which we are able to adapt to. And just finally, to conclude, I have this illustration just showing how different these temporal thresholds are. These are just some people, a few people in this research area and their results, going from delays of below 100 milliseconds to far above 1 second. So there's a huge difference. And it all, in my mind, varies on the task and the interaction and what we want in return. That concludes my talk. Thank you.
Yeah, thank you very much. And we have a question.
You know, if it's being delayed. And then the question is, after the game or whatever, if they stop using it, presumably you would unadapt back. And the question is, how long would that take? And I guess what I'm curious about is if we as in the computing system move towards having things that cause us to do this adaptation, that after we stop using it, that this might cause problems with us doing other tasks.
Well, the adaptation to begin with can take, the after effects persist, but only up until the same. I mean, you have to remove this calibration, you're just exposed to the normal physical delay and with the same number of presentations. So I don't think it's hard to find an effect from temporal adaptation, but to find a persistent one would be more difficult. But as long as you keep the subsequent presentation consistent, I think you will see that it perseveres. And you also find that being exposed to asynchrony in different modalities can affect other modalities. So presenting someone to audiovisual asynchrony can affect their perception between something felt, something tactile, something seen. So it crosses modalities as well.
For us, I guess, when you want to build a system, we would love to have some absolutes, right? That's why everybody quotes Mark's paper about the latency in games, which says 100 milliseconds, that's good. How far are we? Is there any chance to understand what the true answering ranges within a setting? Is there a way of defining within which limitations of what we experience some values can be absolute?
I guess you can get an absolute if you manage to design one specific isolated task. And that's why psychologists, they always run these experiments in very much isolated environments. They remove all the noise. And in that way, you've found thresholds for other sensory integration processes. But for motor visual interactions, we do tend to operate in quite distracting environments. A computer game has a lot of elements in it. And for those kind of situations, I don't think you'll be able to find one. But if you do look at this button press flash situation, I guess with repeated trials and repeated experiments, you could find a universal, an average threshold, but it's not going to apply to every situation. Fortunately, we are distracted by a number of events, so we become more tolerant. In a computer game, there are so many things happen, we tend to engage our attention in the task rather than in the delay.
Thank you for your talk. I just wanted to make sure there is something I understood where I think it was in the game where you have to avoid these objects. You showed that the perception of the people was that it was, they didn't care about the delays, except if it was 500. But you show after that their learning is still less if you have some delays. So if you do a user study, does it mean that if you do a user study, it's not enough to ask the people if that's disturbing? Because in fact, it does impact their learning. Is that true?
Well, that depends on what you're interested in. If you're interested in knowing whether they're enjoying your system, your setup, well, then you ask them that. If you're interested in knowing how it affects performance, then you preferably measure performance. That's why I'm giving this overview, because there are so many ways of addressing the questions, and that's going to affect the results you get. I guess the best answer is to know exactly what you're interested in and what you think could be the most disturbing to what you're wanting to test.
I find kind of disturbing that people don't care, but it still affects their performance, kind of.
Yeah.
Yeah, it seems that this study about delays can explain why our perfectly fast computers of 5 years old looks now very slow. But I wonder if there is at some point some limit where it's not used to have a faster, lower delays, and at some point we stop perceiving the delays.
Certainly. I guess I had one slide, and I guess at the most sensitive, that's why we look at the tactile modality rather than at motor interactions, because that's the most sensitive threshold you find. Where did I put it? There we go. And I only found one study that could yield values this low, and that was the one by Charles Spence and his colleagues. So at the very minimal, feeling something here and then seeing something, at the very minimum, that's 29 milliseconds. You will not find a neural process that's more rapid than that. But for motor visual delays, so actually interacting with the system, these thresholds are higher. So you will easily, I think 100 milliseconds you would easily get away with. You wouldn't be able to notice that. But you can still see an effect of that on performance. But the conscious experience is not likely affected.
how are you dealing with user subjectivity and its influence on finding the threshold window and perception?
There's subjectivity. Well, we average. We, in the study we ran, we had 52 participants. So just repeated presentations and plenty of participants, that will take care of subjectivity.
I think there are no more questions. So thank you again for the talk. Hello. Very good. So, as people are slowly moving in, and I believe some are standing in line for the excellent coffee, I can start to announce the next overview speakers. When you just saw our talk about quality experience, well, it's a topic that has been coming through the multimedia community for quite a while. We actually want to build systems that affect people in the best possible way, or maybe in the least amount compared to what their real experience would be. But the number of us who are doing that for mobile systems is relatively low. And I think that's really something that we should try to learn more about, because more and more of our systems actually need to be performing in the wild on mobile devices. And we should really learn to interact with that and not look at high-powered PCs that are cabled on our desks, even though that's of course also a highly interesting and cool research topic. But, well, looking for an overview speaker for a topic that would bring that together. What we can do with mobile devices and how the changes we make in order to exploit efficiency and still maintain the quality experience. I found that we should really invite Professor Chung-Tak Kim from National Tsinghua University. And well, he has a lot of experience. He's not a classical multimedia systems person, but he was so kind to put his research work together for us to give us an overview. And he brings his colleague, Professor Chung-Han Lin, who is an associate professor at the National Tsinghua University. And they are together going to give us an overview talk, bring together mobile devices and to the quality of experience.
Yes. All right, thank you very much. Hi everyone, my name is Chung-Tak Kim from National Tsinghua University. I'm very happy to be here to give an overview talk. I'm more in computer systems. Therefore, the terms, the terminology that I talk about, for example, like I also use perception, but that is, apparently is different from that you have just heard in the last talk. My collaborator is Professor Chung-Han Lin, so he's from National Taiwan Normal University. Actually, this work is also a joint work by many people. For example, we have Professor Dr. Xu from Academia Sinica, Professor Zhang from National Jiaotong University, Professor Baska Das from Tsinghua University, and we also have some financial support. I think to start with, we know that like mobile phones are actually indispensable in our daily life. Normally, we will bring the phone with us, and we access to a lot of information, to a lot of service through the phones. So we use our phone primarily by interacting with the phone. So by interacting, for example, we instruct the phones by touch, by voice, by buttons, and normally the phone will respond through visual, audio, vibration, and so on. So by interactive, normally that means that the phone is responsive. Okay. So the workload to the phone really depending on how we interact, right? When we touch the button, or what kind of button that we touch, or what kind of activities we work, and then the phone will respond. So basically, if we think about the workload, basically it's very dynamic because it's very difficult to predict. And a lot of times bursty, right? When you have this input, then the system will respond. So it really depends on the user. The different user has different responsive, will have different rate of inputting to the device. So it also depends on the context. So if we think about the workload, if we look at like a classical computer performance equation, it is something like the CPU time is equal to how many instructions we execute and how many cycles we execute per instruction, right? And then divided by the frequency. So if I want, so basically when we say the workload, the workload, for example, instruction count gave you the workload, right? So how many instructions we execute, what type of instruction we execute. And then if we really want to have a high performance, of course, we want to increase the frequency of the processor, and then we can have a shorter execution time, so we will feel that we have a good performance. However, we also know that for mobile phone, performance is constrained by power. So in order to save more power, of course, we want to reduce the frequency, and then this inevitably will increase the CPU time. So the question is, where is the sweet spot, right? So where I should choose the most appropriate frequency so that I can execute the workload. So typical people will constrain one factor and try to optimize one, right? So for example, many people try to say, I want to save a certain amount of power. Then what is the minimum frequency that I can use? Or people said, I want to set the frequency to a certain level, and then what is the maximum power I can save? Or I can use some kind of weighted sum and many other methods. But these are the classical computer system. Basically, the methodology coming from the desktop computers. But if we really want to use mobile phones are really, we say that mobile phones are very interactive. So we must throw in the human factors and consider human satisfaction. Because the user's satisfaction is really what matters about the mobile phone. So the optimization strategy may become that we want to have just enough of the performance before the user becomes unsatisfied, right? So, so if we follow this strategy, then of course we could lower the frequency to a certain level before we know that the user will feel unsatisfied. So basically this is constrain the performance, and then we try to optimize the power. Now, for interactive application, normally the display quality will dominate the user experience. So most of people in this area, when we discuss resource scheduling, we mostly focus on the display quality. And some people will use the term called quality of experience. But actually it is, when we say experience, mainly focus on the display, right? The display quality. So you can say the display quality really depends on the resolution, the frame rate, the image quality. Now, since resolution, frame, image quality basic are the factors like application and the devices. So for the system level, we more focus on the frame rate. So the question becomes that we have three intertwined factors. One is the workload applied to the system. And I want to schedule my resource to work out this workload. But how much resource I should throw in, how to schedule this resource, I'm constrained by the user experiences. So the scheduling problem becomes where I want to schedule the resource just enough that we can execute the given workload. And then this desired quality of experience is satisfied. And then by doing this, we hope that the power consumption can be minimized, because we think that that is the best way that we can do to minimize the power. However, workload and the quality of experience are really dynamic, and they often affected by user context and activities. For example, different applications, like a game. Shooting game and the round-based game are different. Shooting game require you constantly focus on the game. But for a round-based game, you can talk to your friend and then you come back to play, right? For example, Candy Crush, you can come back to do the next move. And then after you finish the next move, you can talk to your friend, you can do other things, and then you can come back to do again. So this type of application really affects how the system, you will respond, you will interact with the system. For example, like if you use the Facebook, there's different type of activity you can do. You can scroll, you can touch, you can watch a short video, you can input your text. So there will be different ways to interact. But a lot of time you can do this without fully focus, concentrate on the screen. And it also depends on the context, time of day. At different time of day, we will use different application. And at different time of day, our interaction with a particular application would be different. For example, if I were on the train, I might read some books, I might read some articles. But while I'm jogging, I like to listen to the music. Right? So there will be different applications that I will use. And then if I'm walking and I still want to read some short message, but while I'm walking, I normally will not read a long article. Right? So even I use Facebook, when I walk or when I sit, I will have different activities to interact with the Facebook. So different type of application we may use with different interaction patterns might be applied. Users' quality experience will also different, right? So as I mentioned, if I'm walking, I don't expect that the screen quality will be that good because I know that because while I'm walking, I'm reading the screen, it is shaking, so I don't expect that the screen really needs to give me that good quality. But while I'm sitting and playing a shooting game, I really hope that the screen quality is very, very good. Right? The resolution, the frame rate is very, very smooth. So you can see that at different contexts, we might have different requirements. So we just mentioned that we have 3 factors, but actually we also need to put up the context as the 4th factors to consider. And at different contexts, we might impose different workload. We might impose different quality of experiences. So how do I know all the relationship between each other? Okay, so these are the issues I don't think I have time to go through, so we will get into some of the topics that we want to cover today. So first we will look at one specific example. Is we look at those devices, right, the display device, and to see what kind of context that may affect and what kind of opportunity that we have in order to optimize the device. Then we will go quickly on the Android display system to see what current practice, how people do, and then how we can do this quality-aware scheduling problems. And finally, how we can collect data. So I will handle the time to Professor Lee. Okay.
Thank you, Professor.